Hello everyone, I'm Xiaoting Shao from Darmstadt University in Germany. I will be presenting our work modeling multivariate ranking functions with MinSum Networks. This is a short paper. So let me first give an overview of our work. This work adapts sum product networks to MinSum networks, and MinSum networks offer a compact representation for the ranking function, and this representation guarantees tractable inference. Besides, the MSNs can be optimized via gradient-based methods because the representation is differentiable. So we want to represent ranking functions. Now, what are ranking functions? First, a ranking function over a set omega is a function kappa that maps an event to a natural number or infinity. At least for one event in omega, the rank is 0. This function is a qualitative abstraction of probability functions. Then naturally it can be used to measure uncertainty, and this uncertainty can represent degree of surprise. That means higher ranks implies more surprise, therefore less likely to happen. Here, we give a quick introduction to sum product networks. First of all, it is a rooted directed acyclic graph. Its leaf nodes represent local univariate distributions. The internal nodes are sum nodes and product nodes. Sum nodes represent mixture, and product nodes represent factorization. Each edge emanating from a sum node has a non-negative weight, and the weights of all descendants of a sum node should sum up to 1. This is important for normalization. So in the end, the network encodes a polynomial in this computation graph, and it represents a joint probability distribution. On the right side is an example of a sum product network. So how is the ranking word different from the Bayesian word? First of all, it has different factorization rules. The rank of two independent events equals the sum of the rank of each event, and the probability of two independent events equals the product of the probability of each event. And the mixture of ranks of X is a minimum rank of all mixture components, and the mixture of probability of X is the sum of all mixture components. For the empty set, its rank is infinity, and its probability is 0. For the entire set, its rank is 0, and its probability is 1. Now that we have enough background knowledge, we introduce our model, MinSum Networks. We will first demonstrate the presentation, the representation, then explain how inference is done. Then finally, how to learn this representation automatically. So MSNs, they are, first of all, also a rooted directed acyclic graph. The leaf nodes represent local univariate ranking functions. The parametric form of these univariate ranking functions will be clarified further later. So the internal nodes are min nodes and sum nodes. Min nodes represent mixture, and sum nodes represent factorization. And each edge emanating from a min node has a non-negative integer weight, and at least one descendant of a min node should have weight 0. So this is important to guaranteeing that there is at least one event in the whole set that has rank 0. So on the right side is an example of a MinSum network. So basically, this is a computation graph that encodes a ranking function. So how do we do inference on this computation graph? Here we use again the same network as example, and we evaluate on the event x1 equals 0, x2 equals 0, and x3 equals 0. So evaluation starts from the leaf nodes, and the values at the leaf nodes are propagated bottom up. Each node indicates a computation. And min nodes takes the minimum rank from all its descendants, and the sum nodes sum up all the ranks from all its descendants. Then finally the value is propagated up to the root node, and this gives us the final rank that we want to compute. So you can see that inference takes only linear time, as it traverses the network only once. Therefore, tractable inference is guaranteed in MinSum networks. Now let's have a closer look on the leaf nodes. So the figure on the left side illustrates this function, and the formula on the right side is the functional form. P is a parameter we want to optimize, and X is the variable we want to model. And we assume this variable is binary here, so either 0 or 1. And C is a scale factor. We set it to 100 here, but you may choose other constants for it. So this function we choose is basically a linearly transformed sigmoid function, and we choose it because it is smooth and differentiable. So this makes optimization easier. But in theory, you may also choose any other function form that satisfies the aforementioned conditions for ranking functions. So let's look at the figure more closely again. The y-axis is output as rank. The x-axis is a parameter p. So as the p slides from left to right, the rank of event x equals 1 first have rank 0. Then it has higher and higher ranks until 100. And for event x equals 0, this is the opposite case. As the p slides from left to right, the rank of event x equals 0 first have rank 100. Then it has lower and lower rank until only rank 0. So each p-value yields one distribution. And for example, when p equals 8.3, the distribution gives rank 100 to event x equals 1 and rank 0 to event x equals 0. So whether this is the most probable distribution given some observed data, the overall rank of the whole dataset will be the objective for the measurement, and it will also guide the parameter p to the value that lowers this objective. At inference time, we quantize the output so that only natural numbers can be propagated up to the root nodes. So in order to learn an MSN automatically from data, we first take an MSN with random structure and random weights. From a machine learning perspective, the problem is then to find the parameters of the model using independent samples from the distribution. That is, we are searching for the parameters that make the overall rank of the observed data on this assumed network minimum. And this corresponds to maximum likelihood estimation, MLE, in statistical inference. So for those who doesn't know maximum likelihood estimation, it is a method of estimating the parameters of a probability distribution by maximizing the likelihood function so that under the assumed statistical model, the observed data is most probable. And we make the assumption that all the training examples are independent and identically distributed. Then the overall rank of the observed data under the assumed MSN structure equals the summation of the ranks of each instance in the training examples. So this is the rule of factorization in ranking world, if you recall. Then in the end, we use gradient-based methods to optimize this objective function. Nowadays, there are plenty of tools to automate this optimization. Most popular ones are, for example, PyTorch and TensorFlow. So we implemented the network as well as its inference routine and learning routine in Python and TensorFlow. Now we present a synthetic experiment and show how the MSNs work. So we construct a distribution with three binary variables. We assume x1 and x2 are dependent, and x3 is independent of any. And this joint probability distribution can be factorized then using the chain rule. Then we generate 300 samples as observed data to learn the MSN's parameters. And this table here shows the counts for every event in the 300 samples and the ranks yielded by the trained MSN. And we expect that the expectation is that the greater count an event has, the smaller the rank should be, because the more often you saw an event, the less surprised you are to see it again. And this is exactly the case for all the possible events here. So our present work is a good start for modeling ranking functions. In the future, we can further explore how to learn MSNs from a probability distribution instead of from empirical data. And we ask ourselves, can we construct MSN structure on the basis of qualitative information, such as expert knowledge? And can we adapt SPNs to represent other representations of uncertainty? So that concludes my presentation. Thank you for listening.